Chapter 11, classroom discussion. Some oscillation problems. Let's see if we can estimate the stiffness of a spring in a pogo stick if a certain mass is given and it bounces once every 2 seconds. Okay, so the key word is bounces. That means you have up and down oscillation motion, and it's once, so one time in 2 seconds. So the time for one complete cycle is 2 seconds. So we call this specific time the period. So the period is given. So it's not specifically saying, oh, the period is 2 seconds. It says it bounces once every 2 seconds, and that's how you figure out that it's actually the period that is given, 2 seconds, because it's one complete revolution or one full cycle for oscillation. This is your oscillation motion. How do we know that it's SHM? No friction is mentioned. So with no friction, up and down or left to right motion, your first guess is SHM, and you just go with SHM because nothing else is on the table here. So the formula for the period is something we're going to use because period is given, mass is given. Clearly you have 2 out of 3 parameters given, so it's easy to solve for the K based on just what's given. So the stiffness of a spring, that stick, the K is the unknown parameter, so square both sides, put K on one side, divide by T on the other side. So pretty much just algebraic manipulations give you the formula, and just plug in what's given. Mass is 32, and the period is 2 to go squared, and you have, what is it, 320 Newton per meters. So once again, remember the stiffness enters the Hooke's law, and the Hooke's law is F equals Kx. Yeah, it's negative Kx, but the point is we're doing dimensional analysis. On one side, it's the force, which is in newtons. On the other side, it's K times X, and X is in meters because it's displacement, or like any kind of change in position because of stretching or compression. So K is newtons over meters. That's your dimensions for the stiffness. Now the spring is vertical and its stiffness is given, and it oscillates with a certain amplitude. Be careful, those are centimeters. You can't do centimeters. You have to convert to meters. And a certain mass hangs from it. Then it goes through the equilibrium with positive velocity at 0. So we're going with 0, 0 here, right? Equilibrium point is 0 and time is 0. You definitely want to go with the sine function. So what's the equation to describe motion, and what is the time when the spring is longest and shortest? So whereas you get to the maximum stretch and maximum compression. Okay, so remember it's a cosine omega t. From lectures we got cosine. This time it's a sine. Why is it the sine? Because of the initial conditions. 0, 0. That means you really don't want cosine. Otherwise, you have to bother with an extra pi over 2. Remember the difference between sine and cosine graphs is pi over 2. You can do cosine, but that will make your equation a little more complicated. You can just switch to sine, and it's perfectly fine to get the equation in terms of the sine function than the cosine. Amplitude, you have to convert to meters. It was 28 centimeters. Now you convert to meters. Here we are. So your capital A, the amplitude value, is already given. So it's A and the sine. Now the only thing that's missing is the omega, and omega is angular frequency for oscillations, but it's the same change in angular displacement with respect to time for rotation. Remember the the radians per second. It's the same thing here. So for one complete revolution, you go through 2 pi radians. This is your angular displacement. This is the time for that displacement. So the omega is just 2 pi divided by the period. And we don't have the period, but we do have the mass and the stiffness. And we already used this formula in the previous problem. Now it's time to use it again. The mass is given, the stiffness is given, so the period is given. So your omega is radical of k over m. So the omega is 2 pi divided by 2 pi, so 2 pi cancels, and it's radical m over k, but it's in the denominator, so you flip it, it's k over m. This is not a typo, it's flipped because the period formula enters the denominator. So you're dividing by this radical, and that means the parameters have to flip if you don't want any denominators here. So k is given, mass is given, you get your angular frequency now. Once again, it was angular velocity for rotation, it's angular frequency for oscillation. And the final equation is A sine omega t. A is given. We figured it out from centimeters. Omega is right here, and t is the parameter. See how it's at any moment of time. Your position, vertical position, can be calculated at any moment of time. This is the final result, the beauty for position equation. Part B was what? At what times will the spring be longest and shortest? So we have conditions for equilibrium given. Now we have to figure out the maximum stretch and compression. What do we know for maximum stretch and compression? We know that if we start from equilibrium, then quarter of a period further in time, well, we'll hit one of those maximums or minimums. And then 2 quarters, we're going to go back to equilibrium. And then 3 quarters, we're going to go to the opposite side. So once again, start from equilibrium. 1 quarter, we go down and hit the maximum. 2 quarters, we go back to equilibrium. 3 quarters, we go, say, up and hit the other extrema, and 4 quarters, we go back to equilibrium. So 1, 2, 3, 4. So if the total period is 2 pi over omega, you can calculate the period because omega is 2 pi over t. So calculate the period by itself. It's going to be 2 pi over omega. 0.174 seconds specifically for this problem because now we know omega. We just figured out omega from the previous part. You say every quarter of a period, you hit the maximum, say, compression or extension, actually, doesn't matter. It's the quarter of a period plus the whole number of periods. 1 period, 2 period, 3 periods. So it's 3 1/4, 4 1/4, 5 1/4, 7 1/4. So every time you have this quarter, you get the maximum compression or extension. And then for the opposite side, you need 3 quarters of a period. Because once again, you start from equilibrium, you go, say, down, that's quarter of a period, you go up to equilibrium, that's half of the period. 3/4 you go to the opposite side, and 4/4 you go back to equilibrium. So 3/4 plus the whole number of periods will put you in maximum compression or extension. Yeah, minimum extension says 3/4, and maximum compression is the other way. So this problem really resembles the problem that we discussed in lecture. There was a question on where are we after a certain amount of time. So if you still have problems understanding the 3/4 or 1/4, go back to lecture notes and practice the quarters and halves of the period for a given setup. Our next problem, now we do have the equation given. We had to figure out the equation before. Now we have the equation, and everything is in System International. You got meters and seconds, which is good, which is the only way to work with. And we have to determine amplitude, frequency, energy, so all sorts of questions to discuss. The amplitude is already there. The easy case is the amplitude. What's the amplitude? It's the value in front of a sine or a cosine function. No matter if it's sine or cosine, the coefficient in front is your vertical transformation. Remember those transformations that you went over in the trigonometry class? Well, now it's time to apply that knowledge. You were tortured for a reason. The coefficient in front, sine or cosine, is a vertical transformation, which is what we call the amplitude. So amplitude is 0.650, and don't forget to add meters because your x and y axis is in meters. Frequency. For frequency, we have to, first of all, it's frequency, not angular frequency, right? The question is for the frequency. It's not the angular frequency. And you can see the connection between the two right here. Remember that omega is 2 pi over t. This is your radians. Those are the seconds. So you go through one complete revolution or one full cycle for oscillations. You travel through 2 pi radians, and t is the amount of seconds that it takes you to do so. So omega is 2 pi divided by t. And if it's divided by t, it's the inverse of t that we get the frequency. And this is the frequency that we are looking for. And omega is the angular frequency, which is a totally different thing. Yes, they are connected, but be careful with notation. Is it the angular frequency, or is it just frequency like we defined it before? So this time it is the frequency, not the angular one. And you solve for frequency. Omega is given. How do we know what the omega is? We take a look at the original equation. Omega is 8.40. That's your angular frequency. And 2 pi is just 2 times 3.14. I keep extra sig figs in the middle. So 1.337 hertz. Frequency is in hertz. This is your inverse of a second. If you're wondering what the hertz is, it's 1 over the second. And now for energy. Total energy. Yeah, total energy and the kinetic energy and potential when x is a certain value. First of all, total energy. For total energy, it's always going to be either mv squared, 1/2 mv squared for equilibrium, or if you are at maximum compression or stretching, it's going to be 1/2 K A squared, the elastic potential energy. All your potential energy becomes total, and you can refer to K or the amplitude from that value. This time we're going to use 1/2 mv squared because you can substitute v, the linear velocity, with omega. Omega was your angular velocity, now it's angular frequency. So instead of v, you go omega a, r, the radius for rotation becomes amplitude as maximum displacement from the equilibrium. And you square the whole thing, so it's omega a squared. So it's omega squared and a squared. And that's it, because you have the omega. Omega is right here, it's given. And a is also given. You can take both values from the given equation and use it to do the calculation for energy. The total energy is 17.1 joules. Yeah, makes sense. It's not too much. Definitely what you expect for a small mass of 1 kilogram oscillating back and forth. So 17 joules, that's the total energy. And then potential energy is 1/2 kx squared, and k is connected to omega. We discussed that connection during lectures. Now it's time to just use, see, we're really playing with the same equations over and over again. It's 1/2 kx squared, 1/2 ka squared for the maximum stretch and compression. And it's 1/2 mv squared if we're talking equilibrium. That's it. The rest is just you really take from the previous discussion, like what is given, what is missing, and you solve for anything that you can possibly wish for. So K is substituted with omega. That's it. You plug in the values. That's it. Mass is given. Omega goes squared. Your 840 is squared. And X is X given. Yeah, it says kinetic and potential at a certain stretch or compression. So 0.36, it's already in meters. So you just plug in X because it's given. Don't forget to square it. It's a very good practice for you to grab your calculator and make sure you're getting the same value here and the same value there, because it turns out that sometimes you do provide me with a good formula and then you fail the calculations part. Make sure you can use your calculator. I'm not joking. It's just really a sad story when you show the correct work and then you lose points because you just can't use a calculator. Practice with your calculators. Make sure you get the same values on your calculator that I have here. Yeah, and what is kinetic energy? Every time you have a certain value for potential, you can say, oh, and the rest is kinetic, or vice versa. What is kinetic? It's the total take away the potential part. So if the total is 17 and potential is at some point is 5, then the remainder is 12 for the kinetic, because mechanical energy is conserved at every time. For simple harmonic motion, it's always like that because there is no friction. With friction, you can't say this. You have to consider change in kinetic energy work done theorem. That would be the best way to handle those cases. Okay, next one is simple harmonic motion. It says specifically SHM, attached to a spring with a constant. And when the object is a certain distance away from equilibrium, it's moving with a certain speed. See how you have the mass, you have the speed, and right away you can say, oh, therefore kinetic energy is 1/2 mv squared, and the rest would be the elastic potential, and the total energy would be conserved. So right away, from what's given, you can figure out what's missing. So what's the amplitude and what's the maximum speed attained by the object? Where is the maximum speed? Where do we hit the maximum speed? You have to remember that. Maximum speed is maximum kinetic energy that happens at equilibrium. At equilibrium, there is zero stretching, zero compression, x is zero, so your energy is all kinetic. And maximum stretch and maximum compression, you stop, so kinetic is zero, and it's all potential. Keep that in mind. So for maximum speed, we have to figure out what's going on at equilibrium. No friction, mechanical energy is conserved, and as I said, it's maximum stretch and compression, speed is zero. This is your conservation of mechanical energy. And if it's all potential, then instead of an x, you say it's the amplitude, because amplitude is the maximum stretch or compression. And that's it. Then you can solve for what's missing. From this equation, you got the mass, you got the speed, you got the k. Do you have the k? Yes, you have the k. Everything's given. Just solve for what's missing. What's missing is the amplitude. So from simple algebra, you solve for a, plug in the values that are given. V is given, stretch is given, everything is given. Boom, you have 5.5 centimeters. Please don't say centimeters. Please convert to System International. Show me the scientific notation. Show me that you know your prefixes. Do not leave as centimeters. Do not leave millimeters. Do not leave mega joules or whatever. Please always convert to System International using scientific notation and sig figs, of course. This is the best way to answer questions in physics and science in general. Yeah, conservation of energy again. Everything's here. But now it is the maximum speed, which happens at equilibrium. It was maximum stretch and compression. Now it's maximum speed at equilibrium. No x, x is zero. So it's all kinetic, and we already have the solution for the maximum speed from lecture analysis, lecture derivation. So you got your maximum speed right away. You figured out the amplitude from the previous part. Amplitude comes from the part A. So you're going to use it for your amplitude value. Stiffness is given. Mass is given. Easy peasy. 0.59 meters per second. Yeah, makes sense. You can double this value, and that would be miles per hour. So if it's 0.6 meters per second, that would be 1.2 miles per hour. So yeah, reasonable for a small mass on a spring, a pretty stiff spring. Yeah, and we are only a few centimeters away from equilibrium. Nothing crazy, no crazy numbers. Okay, now the pendulum. For the pendulum, we got the frequency of oscillation, 2.5 hertz. And it's released from rest starting at an angle of 12 to the vertical. It's very important. Do you remember anything about angles? Remember how it's up to like 15, 20 degrees? You can call it a what? Small angle approximation. And then your reference angle theta in radians is approximately the same value as the sine of theta. And you call it a simple harmonic motion. So you can use all the equations from simple harmonic motion for the pendulum. So what's the position of the pendulum at certain time? Well, first of all, we need the position equation from what's given. Let's go back to our diagram from the textbook for the pendulum. Position is a cosine omega t. This is your general equation. Why is it a cosine? Because we start from the maximum stretch or maximum compression. We don't start from equilibrium, right? So if equilibrium would have been the starting point, then you would have said sine. But as long as it's maximum stretch, you say cosine. Position, see how position, it's not x, it's not y, it's just the position along the trajectory of oscillation. For a pendulum, you can't say x or y, it's just this weird half of a circle, like a curvature of some kind. That's the trajectory, that's your position along this curve. For omega, it's radians per second. You travel through 2 pi radians in one complete revolution, and it takes amount of time that we call the period. So 2 pi over t, or the inverse of a period, that's what we call the frequency, and that's what's given. We do have the frequency given, and that's just linear frequency. It's not the angular frequency, it's not omega, it's the f. And f is right here. That's how you use what's given to create the equation of equation for position at any moment of time. Yeah, we have the definition of a radian. Radian is arc length divided by the radius. What is the radius? The radius is the length of a pendulum, and this is your arc length. And theta is the reference angle in radians. That's very important, because if it's not in radians, you can't use the small angle approximation. So this time it is radians, all radians. So the maximum position is 1, 2, 1, 2. Sorry, the headset turned off again. So maximum change in position is the radius, which is your L, times the maximum angular displacement, which is maximum angle that is given at what? 12 degrees. Be careful, you cannot do degrees, you have to do radians, of course. You have to convert it into radians. Theta must be in radians. So your S of t is just L times theta on the left, and it's a cosine omega t. Well, maximum compression or extension is what we call the amplitude. So amplitude is just S max, which is L theta max. So instead of an amplitude, you say L theta max, and it's a cosine. And instead of omega, we say 2 pi the frequency, and frequency is what's given. This is the frequency that we have given, times the moment of time that we're looking for. Fun fact, the length disappears, it cancels. So the length of a pendulum is not important. It's not given, but it's not a big deal. It turns out it's not going to be affecting our angular position equation. Multiply both sides by 100. Oh, yeah, you have to convert to radians. You can't do, I mean, yeah, if you multiply this by this, then you're going to get angles in degrees. You actually don't have to do it. I would rather leave it at radians, everywhere radians. But in here, I'm just trying to show you how you can use what's given in terms of angle as is, as 12 degrees. Don't do it, just keep it in radians. Convert 12 degrees into radians and do it like that. That would be a better way. I'm just trying to simplify everything in terms of you solving it, but your best bet is look at this equation. You have theta. You have theta maximum. Theta maximum is 12 degrees, but you can't do degrees. Keep it as radians. Convert that 12 degrees into radians. Don't use 12 degrees. And you will use the 2 pi times the frequency. Frequency is what? 2.5. So Yeah, 5 pi is what you get from the given frequency. And then you just plug in the values. Whatever the values are for the time, you will calculate the angular position. Of course, it will be radians. If you want degrees, then you have to convert from radians to degrees. So theta at this moment of time is the radians that you get from 12 degrees times the cosine 5 pi times the moment of time that we are looking for. Moment of time is quarter of a second. So quarter of a second is what you get, is what you substitute for time right here. Let's analyze the result. It's a negative. Negative means we are on the other side. We do have positive side and a negative side. So if you get a negative, that means you're on the other side from the equilibrium position. You have maximum positive, equilibrium, and maximum negative. So you have to, you can't ignore the negative. Negative also is important. Don't just throw it away. At 1.6 seconds, it's the same 12 degrees in radians. Then the cosine, 5 pi is the given frequency multiplied by 2 pi radians. And 1.6 seconds gives you pi over 15. So now it's a positive value. That means you are on this side of the equilibrium position. So you're to the right of equilibrium. In the previous part, you were to the left. Now you are to the right. And at 500 seconds, same thing. You have 12 degrees converted into radians. Cosine 5 pi times 500 seconds. Still pi over 15, still positive. Well, that's just the coincidence. But the point is, once you got the general function, you can solve for any moment of time. Any moment of time is good for figuring out the angular position. I should admit that this is somewhat tricky and challenging problem. Do not panic. You will not see something like that on the test. You have to be familiar with conservation of energy. That's what I'm looking for. And for pendulums, think about the simple pendulum formula. You have the 2 pi radical length over the free fall acceleration. That's the formula you will use. Yeah, and now for waves, like I said, the only formula I really want you to keep in mind is the speed of your wave with respect to the frequency and the wavelength. Wavelength, speed of a certain wave, and the frequency. This is your interconnection, which surprisingly is what you see in your car stereo. Have you ever wondered what your car stereo shows you? Like 102.7 Kiss FM or whatever is the. What is the 102.7? Have you ever wondered that? Well, it is the megahertz. And mega means what? Million. You have 10 to the power of 6 in front, and hertz represent the frequency. The frequency that you see in this little formula is what your car stereo shows you. So based on this frequency and the value for the speed of light, because radio waves are electromagnetic waves and they travel at the speed of light, you can calculate the wavelength of a radio wave of your favorite radio station. So let's do that. You have, so what is the wavelengths for frequency? Yeah, by the way, AM stands for amplitude modulation and FM stands for frequency modulation. So it's the frequency that you play with, and this gives you the range of megahertz versus the amplitude that is changing for kilohertz. Okay, enough of radios. Just for this one formula, single formula, plug in your speed of light, which is 300 million meters per second. That's the fastest you can go with. You can't travel faster than light. That's one of the postulates from Einstein's theory of relativity. Over the kilohertz or megahertz for what you have for frequency modulation for FM range, you can see that you're approximately at 3 meters. So the wavelength of your favorite radio station starting here, goes up and down and back to equilibrium, and this distance would be the 3 meters. So one period would be 3 meters long. That's it. So one little formula explains a lot for connections between different parameters of waves, specifically mechanical waves, electromagnetic waves, sound waves. Just be careful, the sound doesn't travel at the speed of light. So mechanical waves, they don't travel at the speed of light. But electromagnetic waves, yes, they do. It's the speed of light. And radio waves are the electromagnetic waves. You have radio waves, microwaves, infrared, visible light, ultraviolet, and X-rays and gamma rays. Those are the candidates for the speed of light. They travel at the speed of light. Electromagnetic spectrum. Anyways, that's it for chapter 11. Like I said, the last 5 sections are out, so do not worry about those problems on the test. We'll stop recording here.